I'm Mr. McBrien. This is SCH4U, Development of Modern Atomic Theory. Really where we should start, at least briefly, is to talk about the early models of what matter is. So early theory began with a guy named Democritus, who proposed that matter could be divided into smaller and smaller pieces, but that eventually you'd reach a limit where if you broke that up into smaller pieces, it would no longer be the same thing. Now, he even coined the term the atom to describe this indivisible thing. What's interesting is that theory was essentially abandoned, and for almost 2,000 years it was accepted that there were four classical elements, and mixtures of these created anything you could name. So you could mix together fire, earth, water, and air in varying proportions in order to get iron, water, or what have you. And this theory, in fact, remained until the late Middle Ages, so for a very, very long time. Now, in 1803, along came a guy named Dalton, who he revived this atomic theory of matter and used it to explain several chemical laws that were compiled together. The law of conservation of mass from Lavoisier, the law of definite proportions from Proust, and his own law of multiple proportions. Now, when you put all this together into a billiard ball kind of model of indivisible atoms of elements, you could look at this and talk about combinations of these billiard balls to form various things about which we know. And so this is one of the early diagrams of this, talking about fitting together these billiard balls to make varying things. And in fact, this was a remarkably perceptive model for the substances, the compounds that we know of today. And so this model remained largely unchanged, if not completely accepted, largely unchanged, for, again, almost 100 years. In 1897, Thomson proposed something slightly different. And this was based on the idea of electricity, and Faraday and Arrhenius essentially proving that electric charges are part of matter as we know it. So Thomson took a thing called a cathode ray tube, and he managed to measure the mass of a beam of negative particles in this tube. He didn't actually measure the mass. He measured the mass to charge ratio, but this was a remarkable achievement. He determined that these tiny particles were coming off of matter, and he called them electrons. And so this idea that charge was part of matter needed to be integrated into our existing billiard ball model. And so he came up with this famous plum pudding model for the atom, in which you had a mixture of positively charged stuff, the pudding, and these negatively charged particles inside it, the plums. And so this did a good job of explaining the creation of positive ions. You could kick an electron out of this plum pudding and create an ion. It also did a reasonable job of explaining conductivity, because you could you could hop these electrons between the individual atoms. So this did a really good job of explaining various parts to do with charge. Okay, so now we have this new plum pudding billiard ball thing, and along comes a guy named Rutherford. Now, Rutherford was interested in the idea of radioactivity, alpha, beta, and gamma rays, and using those to interact with atoms to try to give further insights into what these things were, these atom things. And so he took an alpha particle emitter, essentially a source of radiation, and he proposed that these alpha rays that are essentially very high energy helium ions. So they have a positive charge, and he proposed that these high energy particles would just go straight through an extremely thin sheet of gold foil. And based on the model of plum pudding, this seemed very reasonable. So what he did was he designed a detection screen that was 360 degrees around a piece of gold foil, shot the alpha particles at the gold foil, and he could use this screen to detect the alpha particles. And what, of course, he expected to see was that there would be all these alpha particles would be hitting exactly on the other side, going straight through the gold foil. Now, what he saw was not that. So this is a combination of his conclusion and the result. So the expected result with plum pudding was that the beams would just pass straight through the atom, and there would be no significant deflection of these beams. What he saw was that was actually the case. Most of the beams went straight through. But every once in a while, one of the alpha particles was deflected. Now, this result was entirely inconsistent with the plum pudding model of the atom. If the plum pudding model were there, you'd see a consistent layer of material all the way through. And, okay, maybe you would see deflection, but you'd see deflection of everything, not once in a while a single deflection and the majority of them going straight through. So this result that he saw, caused them to revise the model. The plum pudding model could no longer be there. Now, so his planetary model came out, was released in publication form in 1911. Now, that's what's interesting. You can see how quickly things are accelerating. We were measuring in thousands of years the progress. Then we were measuring in hundreds of years the progress. And now things are happening so fast that we're seeing results coming out almost in the same year. Changes to the models are happening. Okay, so Rutherford's planetary model, he decided that the only model that was consistent with this deflection of a few of these alpha particles was if the positive charge in the atom was a very tiny, dense nucleus. And based on the number of alpha particles that was deflected, he concluded that more than 99.99% of the atom had to consist of simply empty space. And his theory was that electrons were orbiting the nucleus at a large distance. If we do the calculation, realizing what the mass of the electrons is, the charge to mass ratio of the electrons, he took that plus the fact that more than 99.99% of the atom was empty space, and he was able to calculate that a teaspoon of atomic nuclei would weigh 6 billion tons, or about 900 of the pyramids. So this is an extremely dense material in the center of this atom, in this nucleus. So his planetary model had to incorporate the idea that there was positive charge in there, and Rutherford proposed a few years later that there would be a positively charged particle called a proton that would offset the negative charge of the electron. It took another 18 years for Rutherford and Chadwick to find that there was an uncharged neutral particle as well, called a neutron. So this, then, was the kind of model that Rutherford put together. And electrons orbiting a positively charged nucleus. And if you remember your early physics stuff, Coulombic forces would have the negatively charged electron attracted to the nucleus. Well, the basic theory was that the electron was moving fast enough that it could offset this attraction, much like a satellite offsets gravitational pull due to its speed. So, and if you wanted to get really tricky, you could even calculate the speed of the electron based on the distance. But don't bother going and doing that work, because what we're going to find is that the truth is something slightly different. Okay, but let's go back a little bit. So what we get to then is the idea that by 1932, we've got 3 subatomic particles that form up the atom. This indivisible thing is actually the sum of 3 different kinds of particles. We've got a heavy, positively charged proton with a mass of about 1 AMU, atomic mass unit. A neutron, heavy and dense, with a charge of 0 and a mass of almost the same amount. And then we have this negatively charged electron that is outside the nucleus with a -1 charge and a much smaller mass. Okay, the planetary model, as I mentioned a few seconds ago, had some problems. And the problems had to do with this orbiting process. A satellite doesn't have a charge, and it orbits the Earth for a very long time, almost indefinitely. Satellites can orbit the Earth. In fact, the moon does, right? However, electrons have a charge. And according to classical physics, anything with a charge that is accelerating should emit light, should give off energy. And the law of conservation of energy suggests that if this is happening, the energy loss would result in a loss of momentum. This loss of momentum would cause the electrons to spiral into the nucleus, and the atom would collapse, and bad things would occur. And this clearly doesn't happen, at least not on a time scale we can measure. And so the planetary model clearly is missing some key piece of information. But there's something else. The other piece of the puzzle had to do with these electrons when we give them very high energy. When we give them high energy, the planetary model would suggest that you would see a continuous spectrum, a broad spectrum of what we call white light, and we'll talk about that a bit more. But this isn't what occurs. Instead, we see certain frequencies only when these electrons are excited. Now, what does that mean? Well, a satellite in the planetary model can be at any distance from the planet. Its speed changes a little and that offsets it. But this fact that the emission spectrum of elements is at discrete intervals suggests that only specific orbits would be accepted in the planetary model. And there's no model for this in Rutherford's approach. Okay, so we need something more. Before we talk about this, it's a good idea for us to talk about the nature of light and some things like that. All right, so first off, let's talk about one of those classic light bulbs that you'd be hard-pressed to find in your house these days. So light bulbs emit radiation, EM waves, light, based on being heated up. It's called black body radiation. And when you do this, you get a spectrum that is essentially white light. Put it through a prism, it splits, and you see all the frequencies. And that is what white light is. So, if you heat up an object, you get a broad spectrum of light. However, if you heat up a gas that is in relatively low pressure, it emits energy too, but something weird happens. When we run it through a prism to see what frequencies we get, we only get specific frequencies. There's only a few frequencies we receive. And this is really quite weird. Perhaps just as interesting, if we shine continuous light through a cold gas, it absorbs certain light. No great shock there. But what's interesting is it absorbs exactly those frequencies. So this gas has some kind of fundamental interest in these frequencies of light. Now, why? Well, oh, and one more thing. You change the gas, and that line spectrum changes. You still get a line spectrum, but they're different frequencies. So this is a very interesting result. And this guy, Niels Bohr, decided to go and look at these and try to use this as a further clue for the nature of the atom. So each gas has its own unique emission spectrum, and its absorption spectrum is almost the mirror image of that. Why? There's nothing in that planetary model that would explain this. So let's diverge a little further and let's talk about the wave theory of light. Light's a form of electromagnetic radiation. All EM radiation is made up of electric and magnetic fields that oscillate in a wave pattern. And it travels at a very famous constant speed in a vacuum. The wavelength and frequency of this wave can change, but the speed is constant in a vacuum. What is that speed? Well, it's the speed of light, symbol is c, and it's 3 times 10 to the 8 meters per second. So what is that? That would be 300 million meters per second, or 300,000 kilometers per second. Now, any wave has a wavelength and it has a frequency. So what's interesting is that whole spectrum that we talked about all has to do with the wavelength. So if we have short wavelength, we have blue light, and if we have long wavelength, we have red light. And the classic wave equation describes light as well. So the wavelength is equal to the speed divided by the frequency. Now, light is just a subset of the full spectrum of electromagnetic radiation. So we run right from gamma rays over here where the wavelength is very, very small, through X-rays, ultraviolet, if you want to work on your tan, the visible spectrum through here, infrared, radar, FM, TV, shortwave, and AM. So radio waves, etc., all of these things are just light at different frequencies. And light is in fact a very tiny portion of the EM spectrum. Okay, we won't go into this in too much detail, but you can examine this at your leisure to talk about wavelength versus frequency. They're inversely proportional, though. You can say that if the wavelength goes up, the frequency is going to go down. Okay, so this light stuff is extremely useful for examining the atom. This guy, Max Planck, he realized that the spectrum produced by white light, while we often call it continuous, it isn't precisely continuous. So white light looks continuous because it's the sum of a whole lot of these little things called photons. And these photons are a little packet of energy. And so if we look at different colors, well, those colors are individual photons with different amounts of energy associated with them. So the energy of a given photon is proportional to the frequency, and we get to this idea of we can calculate this energy. So the energy of a given photon can be expressed in terms of the frequency and Planck's constant. So we can calculate the energy now of any photon. And in fact, if we have a mole of photons, all we have to do is just multiply it out. So using these formulae, we can do questions like this. We can calculate the wavelength of FM 99.1, which has a frequency of 99.1 megahertz. We can calculate the energy of one photon that is emitted by their transmitter. We can also calculate the energy of one mole of photons that come from their transmitter. And all these things can be done using the simple equations down here. Okay, so how does this relate to the atom? Well, Bohr in 1913 said, okay, based on these spectra, we need a new model of the atom. So we need something that will make this atom not collapse, and we need something that will explain those emission spectra that we see. So his first postulate was that electrons can only move in certain fixed orbits. So this was fairly consistent with the planetary model. So the orbit corresponds to a specific energy level, and an electron can move within that orbit without losing any energy. There's some problems with that, but because we ask ourselves, why can it move without losing energy when we agreed that it can't? But it is a postulate, and he had it. And then his second part of this was that electron can only move from one orbit or energy level to another when it gains or loses energy. And this is the brilliant part of it. So what this did was it gave us a perfect model for explaining these spectra. Because what would happen is our hot gas would every once in a while have an electron move from a high energy to a low energy level and give off light. So in our discharge tube, we're putting in lots of energy, which the atoms absorb, but then they drop down to lower energy levels and they give off energy, and only in the specific frequencies. So this did a very good job of explaining the spectrum of hydrogen. And the fact that there were only 4 visible lines was perfectly comprehensible because there were only certain energy transitions that could be made. And so only certain colored lines were observed. So he concluded that there were permitted energy levels And only these energy changes were going to exist, and therefore you'd only see certain colors. And the Rydberg formula described that. And you could go further and you could calculate the energy of an electron based on its orbit. So you could essentially take this simple formula, negative 1312 divided by n squared gives the energy. And you could even calculate the transition energy then, because you could say, well, when it goes from level 1 to level 2, you could calculate the energy that was released. So the Bohr model did a great job of explaining the hydrogen spectrum and explaining why different elements have unique spectra. Interestingly, too, it explains Mendeleev's periodic law, talking about the filling of energy levels. But it still had some problems. The biggest one was that his calculations only worked for one electron systems. So you could have a hydrogen atom. You could pull one electron off a helium atom and it could explain it. Or you could pull two electrons off a lithium atom and it would explain it. As soon as there were multiple electrons in there, the calculations didn't agree with experimental results. And a similar problem existed in that the visible spectral lines of hydrogen could be split by electric or magnetic fields. Well, this isn't a shock because probably those extra electrons are just that kind of electric or magnetic field, produce that electric or magnetic field that wrecks the model. So, the Bohr model, though, was a tremendous leap forward and the first step in quantum mechanics, our current atomic theory. So another sample problem for you to think about, we should be able to calculate the frequency and wavelength of electromagnetic radiation emitted from a hydrogen atom if an electron moves from the third energy to the first energy level. And the calculation is simple algebra and it's given here. Go ahead and pause it if you want to have a look. Okay, so this was really intended as an introduction to the idea of the atomic model. Tough to summarize everything that we've gone through here. You should be able to discuss these models and the assets of them and the problems with them for purposes of testing. So we today have been through Dalton's billiard ball model, how Thomson modified it to come up with the Plum pudding model, Rutherford's planetary motion model, and Bohr's model. And tomorrow we'll start talking about the quantum mechanical model in a bit more detail. We also need to be able to discuss the characteristics of light and how it contributed to our understanding of the atom. Thanks very much. Don't forget to read over today's note and complete the worksheet. Have a great night.